So this activity is just meant to reinforce what we just talked about in terms of state space and transfer functions and being able to switch between them. Here I'm giving you a second order state space system, and your job is to find the transfer function that corresponds to the state space system. So I'm reminding you of a handy identity that comes specifically for second order systems, how to find its inverse easily. So go ahead and give this a shot, and then we'll talk about some of the interpretation we can get leading into the next class. So for this example, what we're interested in doing is taking and identifying our A matrix, our B matrix, and our C matrix, and then computing what our transfer function is based on this formula that we came up with in the previous video. So what we're interested in doing is then computing C multiplied by SI minus A, taking the inverse of that, and multiplying by B. So if we're just interested in computing what SI minus A inverse is, so remember SI is simply just the 2 by 2 matrix S multiplied by the identity matrix, so like that. And that is just S0, 0, S. So when we subtract away A, this is A up here, then we just get S minus a negative 7, minus a negative 12, minus 1, and S minus 0. And now we want to take the inverse of that, and that's where we can apply this, this rule that essentially just holds for second 2 by 2 matrices. So now this is actually the determinant down here of this matrix. So it's just this product minus this product. And then we just rearrange the entries. So that gives us the inverse. And now what we're going to do is we're going to multiply that, pre-multiply by C and post-multiply by B. So this is just a number, so we can pull that out front. This is C. This is the term that's left from SI minus A inverse, and this is B. And so you could take the multiplication in any order, but let's go ahead and take the multiplication of the last two terms. So again, a sneaky way to do this multiplication is, since this is a 0, it's going to multiply this whole column, so that clears it all out. This just multiplies the first column, and so it picks out this 1, 0 actually just kind of picks out that first column from that matrix. So now I'm going to multiply 1, 2 by S1, and so that gives me S plus 2. So that appears in the numerator, and then I divide by this denominator. And so this is our transfer function. So that's the end of the activity. I'd like to show you some interesting observations that leads into the material that we'll get into in the next section of the class, which is really understanding the behavior of these systems, is to take a look that we can factor this denominator into two terms because it's a quadratic, and it's going to be S plus 3 and S plus 4. And so that means that the roots of the denominator are as S is equal to minus 3 and S is equal to minus 4. And so now if we take a look, so that came out of the transfer function. So if we now take a look at our state space representation, if I look at the eigenvalues of the matrix A, so that's the state matrix in state space form. So the way that we find eigenvalues is we find where the determinant, what values of lambda, the determinant of A minus lambda I are equal to 0. I can go through this math, and that already kind of, you see some of this characteristic A minus lambda I, SI minus A inverse. So you see some common features here. So if we go through that math, what ends up happening is A minus lambda I get essentially a very similar matrix that we got before, and we're going to take the determinant. So again, we're taking this product minus that product. It gives me this. I'm going to expand that out, and now I get essentially the same polynomial that I had before right here. I can factor that, and now I get eigenvalues of the matrix A that are minus 3 and minus 4. And so this connection that we're seeing here is not a special case. This is in general, we will find this, and now this gives us a direction to look for as we start to think about characterizing the behavior of these systems and how we can see similar information across the different representations that we're working with. So that's where we're moving in the second part of this class. The last thing to mention here is that MATLAB actually has a way to transfer nicely between state space representation and transfer function. And that means you specify your matrices, A, B, C, D, and that will output the numerator and denominator of your polynomials that are in your transfer function.